Hello and welcome to Kognito Key. I'm so thrilled to have you here today. If you've ever worked with high-frequency circuit theory, you've probably felt like achieving true precision is kind of like chasing a ghost. Well, today, our mission is to finally capture that precision. We're going to dive right into a brilliant piece of engineering called the Wagner earthing device. It's essentially this incredibly clever solution explicitly designed to eliminate stray capacitance. By the end of this explainer, you'll know exactly how and why it works so perfectly. Let's get started. So let's get right into it. Why exactly do precise measurements just seem to fail at high frequencies? Well, it's because your circuit isn't just made up of the components you actually intended to place there. There's this invisible enemy lurking around, stray capacitance. We're talking about these tiny unintended capacitances that just naturally get induced between the elements of your bridge, between the different arms, and yes, even between the bridge and the ground itself. And because these stray elements mess with the overall impedance, they completely throw off your measurements. It makes getting a perfect balance feel basically impossible. To put it formally, stray capacitance is an unwanted high-frequency element that introduces measurement errors straight into your circuit. And honestly, without managing this, the high-frequency communication devices we literally rely on every single day, they just fail. Now, sure, enclosing your elements in a shield definitely helps mitigate this, but let's be real, it's really only a band-aid. If you want to completely eliminate these errors from throwing off your balance, you need the ultimate tool for the job, the Wagner earthing device. Fundamentally, the Wagner earthing device is a highly specialized voltage divider circuit, but here's the cool part. Instead of just passively blocking stray capacitance like a shield would, it actively integrates right into the circuit. It's there to mathematically and physically cancel out the error. It's explicitly designed to sit right between the elements of the bridge to provide absolute, high-accuracy balance. It's honestly an elegant work of circuit theory. To really appreciate it, let's break down how it's actually built. All right, let's look at the construction. First, we have our four main impedance arms of the primary bridge. That's Z1, Z2, Z3, and Z4. Then we bring in the Wagner device, which adds two more variable impedance arms, Z5 and Z6. Now notice how the impedance of these Wagner arms is actually pretty similar to the main arms of the bridge. They contain both resistance and capacitance. But here's the absolutely crucial part. The exact center point between Z5 and Z6 is firmly earthed. Finally, we drop in our detector, labeled D, spanning right across the center. You can kind of think of this whole setup as a high-stakes tug-of-war. Our main bridge, using impedances Z1 through Z4, is desperately trying to find that perfect balance condition. But those pesky stray elements, capacitances C1 through C4, are actively working against us. They're basically creating chaos and preventing that balance from happening. Enter the Wagner impedances Z5 and Z6. These are our secret weapons, positioned in a very specific way to force the bridge into balance, completely regardless of those stray elements. So how does it work in practice? Well, achieving this balance is actually this really fascinating iterative dance. First, you adjust the main arms, Z1 and Z4, to get the bridge as close to balance as you possibly can. Then, you throw the switch, labeled S, over to the earth connection, which is E. Next, you adjust the Wagner arms, C4 and C5, until you hit the absolute minimum signal on your detector. Finally, you reconnect the switch back to the main bridge and just repeat the whole process. You keep switching back and forth, refining your adjustments every single time. Now here is where it gets really interesting. For high-frequency bridges, the detector is very often just a set of headphones worn by the engineer. This creates a uniquely intimate auditory feedback loop. As you continually throw that switch back and forth, making those tiny impedance adjustments, you are literally listening to the electrical current. You repeat this iterative process over and over until that minimum sound becomes completely silent. When there is absolutely zero audio coming through those headphones, you know for sure you've hit the mark. And when you finally achieve that silent sound, something magical happens mathematically. Perfect balance is achieved. Because of those precise adjustments you made to the Wagner arms alongside the main bridge, the points B, D, and E all drop to the exact same electrical potential. And as we know, with no potential difference, current simply cannot flow through those stray elements. The error completely vanishes. Stray capacitances C1 through C4 are entirely eliminated from the bridge circuit equations, right alongside Z5 and Z6. The result? Your measurement is flawlessly accurate. Isn't it just incredible how matching electrical potentials can completely silence such complex measurement errors? That is the true power of the Wagner earthing device. If you found this explainer helpful, please hit that subscribe button for Kognito Key. And don't forget to like and share this explainer with your fellow engineers and classmates. But before you go, I want you to think about this. As our technology pushes into even higher, completely uncharted frequencies, what new invisible enemies are we going to have to outsmart next? Keep learning, keep questioning, and I'll catch you in the next one.